So we have a Professor Francois Gueritaud again, and he will again talk about the introduction to co-compact and Anosov action. So this will today will be part 3 and 4. Okay, so please go ahead.
Okay, thank you very much for this opportunity to speak. So here's I recall the plan of today. There will be a big first part on symmetric spaces and trying to build intuition on how to move in the symmetric space of SLN and the group SLN or PSLN, and there will be another part about so where we will define what Anosov representations are in general and how they act on the symmetric space. So here's the main takeaway of the last 2 lectures from last week was that convex co-compact is a condition on representations that is good in the sense that it's an open condition. If you have a convex co-compact representation and you deform it a little bit, it's still convex co-compact and dynamically stable. A class of representations from a word hyperbolic group into the isometry group of a word hyperbolic space or delta hyperbolic space. So everything is hyperbolic. Then there's a notion of good representations of gamma into isometries of X. So the main example again was hyperbolic space Hn and actions of gamma on it by isometry. So basically hyperbolic N manifolds. Now the main takeaway of today's lectures is going to be that Anosov representations are a generalization. It's a slightly sophisticated generalization. The most naive generalization of convex co-compact doesn't work. But this sophisticated generalization is the correct one in the sense that it preserves openness in particular. Generalization to what? Well, there will still be representations of a gamma into a G. The gammas will be the same. It will still be word hyperbolic groups. But G will now be essentially SLN, PSLN, or in general, what's called semi-simple Lie groups. So, okay, so then that's higher rank generalization. What do we mean by higher rank? Well, the rank is an integer. When you have a semi-simple Lie group, there's an integer called the rank, and we'll see what it is based on examples. Essentially, when you have a symmetric space of negative curvature, the rank is 1. And when you have a symmetric space of non-positive curvature, I thought I wrote that. Yeah, with non-positive curvature, the rank is at least 2. And again, we will focus almost exclusively on PSLN, maybe the products of a few PSLNs, which is also semi-simple, and work mostly from examples. Okay, so here are a few reminders about the case PSL2. So this should be familiar. It's the case of the hyperbolic plane. PSL2 acts on the hyperbolic plane in the familiar way. A matrix A, B, C, D takes a complex number Z to AZ plus B over CZ plus D, where A, B, C, D are real. And I guess we have to say the determinant here is positive. And I'd like to summarize a few of the features that we want to have in mind when we generalize later. So here is, for example, how a diagonal matrix acts. If you take E to the A over 2 and E to the minus A over 2 on the diagonal, that translates by a distance of A in the hyperbolic plane. It translates along this line, the reference line from 0 to infinity, as a base point at complex unity, and a line through the base point, and we translate by a length of A. And next to this, I've drawn the disk model, which is a little bit easier because we see all of H2. What it looks like is that there's this base point at the center, an axis through the base point, and we translate along that axis. So those are the diagonal matrices, which of course exist also in the SLN. So we're curious how that generalizes. Here is how a rotation matrix acts. It also fixes the base point. Well, it fixes the base point and rotates by an angle. I have to be careful. There are two little booby traps here. The angle of rotation here is theta, but the matrix here is a rotation matrix with theta over 2. You've got to get used to this over 2. It's present. One way of remembering it is that if you make theta equal to 2 pi, then here you have cos pi, so that's minus the identity, but minus the identity as a Möbius transformation acts like the identity. So hence the over 2. And the second little booby trap is that if you look carefully, the minus needs to be here, not there. Usually a rotation of angle theta, it would be the transpose of this matrix, theta over 2. But due again to the way that these Möbius transformations are defined, the minus actually needs to be here. For example, for small theta, 0 moves a little bit to the right, so that you can get this over that, sine over cosine. Okay, so those are the rotations. And the third type of motion that's interesting is by what's called parabolics. So those are matrices conjugated to unipotent, 1 on the diagonal and 0 below. And the way this acts is by, well, you push along what's called a horocycle. Again, all of this should be only a reminder. And the way this acts on the hyperbolic plane is, well, a horocycle looks like one of these circles tangent to H2, and you translate along it. While pointing, this whole group here fixes that point at infinity, so the little arrow continues to point all the time towards the semi-ideal point. And of course, you also have the lower unipotent matrices. Those are going to fix the opposite endpoint of the reference line. And it's interesting to note that these two types of motions are well, this one turns clockwise and that one turns counterclockwise. So in PSL2, which is the oriented isometries of H2, they are not conjugate. They are conjugated to each other in PGL2, but not in PSL2. Okay. Now, there is these basic motions are, you can combine them to move any point to any other point by any path that you like. Here I've drawn a path. If L sub A is a translation of length A along the home axis, and R sub theta is a rotation of angle theta around the home point, then I can advance by A1 units of length, turn by angle theta 1, advance by A2, turn by angle theta 2, advance by A3, and so on. And this is going to take the point P to a point Q. And I would like to invite you to guess or to figure out what Q is. Is it P, to which we have applied L A1 R theta 1, LA2 R theta 2, LAN R theta n? So in the order, sorry, in the order that the information can be read here from P to Q, or do we need to multiply from the right? It's worth doing this at least once in your life if you never have. Would anyone like to suggest which of these two is correct? I think Zoom allows you to take votes, so we could make a vote. I'm going to vote today. So this one is false. This one is correct. It is, in fact, in this order. You can convince yourself that, for example, the point is that these maps act on the whole plane. And when I look at a path like this, I'm more thinking of moving a point in the plane as opposed to moving the plane around the point. This is sort of what causes the reversal. Okay. Now, another feature in the list of familiar hyperbolic facts that I'm going to want to generalize is the whenever you have two lines, two geodesics of the hyperbolic plane that become epsilon close at one point. So by epsilon close, I mean they pass through closed points and they are also epsilon close directionally. Right? So two lines that come very close, that form a big angle, that doesn't count as close for me. If they become roughly epsilon close in space and directionally, then they stay close for roughly log epsilon units of length. Log epsilon in absolute value. So and that's the point at which they start to separate. They become distance 1 apart, and then their distance grows linearly. On either side of the point of close approach. Of course, one of the two sides could be much longer. For example, they could be infinite. You could have two lines that are asymptotic that share an ideal endpoint at infinity. And then the rate at which they become closer is exponential. Depth t, they're roughly e to the minus t close. All right. Now, about higher rank. The main idea is that when you have a group, again, I'm going to focus essentially on PSLM, but in general, I could say a semi-simple Lie group or reductive Lie group. To that group is attached a symmetric space X. What is X? It's just G modulo the largest compact subgroup that you can find. Turns out that in this class of groups, the largest compact subgroups are all conjugates, so it doesn't matter which you choose. And you mod out by something compact, as big as possible, and what's left is a Riemannian manifold, well, a simply connected Riemannian manifold of dimension n squared minus 1 of non-positive curvature. It's a manifold whose job in life is to come with an action by G. So whenever you have a representation into G, you have an action on this space. And because we have a strong, we tend to have a stronger intuition of space than of algebra, very often people prefer to focus on the symmetric space instead of the group G, but it's really essentially the same datum. The job of this space is to be acted on by G, and by acted on, I mean in a nice way. It's acted on properly. Well, point stabilizers are compact, and in fact, for any compact subset, it's moved away by all but compactly many group elements. Right? For every K compact, the set of elements G's that fail to carry K off from itself is compact. So the case of H2 was exactly the symmetric space that you get for PSL2. And the question now for us, of course, you could use this formally. And the question is, how can we visualize this quotient, this thing as a space? Again, it's a ball of a certain dimension. Well, I didn't say so, I just said simply connected, but it's in fact a ball of a certain dimension. And we want to describe how to move around in it. So how can we visualize X? I'm going to give three sort of approaches, A, B, and C. So little a, you can see X as the space of ellipsoids in Rn. By ellipsoid, I mean unit volume and centered at the origin. So an ellipse in R2 is the image of a disk under a linear map, and similarly, an ellipsoid is the image of unit Euclidean ball under a linear map. And of course, the Euclidean ball has it has a whole continuous group of automorphisms. So all ellipsoids also come with their copy of SON automorphisms acting on them. Okay, so that's a space. The space of such ellipsoids. And I declare that the distance between the home ellipsoid, B for unit ball, the Euclidean unit ball, distance between the home ellipsoid and an ellipsoid E is going to be just a list of logs of axis lengths. Right? So when you have an ellipsoid in R3 like this one, it has a longest axis that we call A1, a second longest axis perpendicular to the first one, which we call A2, and the shortest axis that we call A3, perpendicular to the first two. And that's completely general in dimension n. You can list the axes from longest to shortest. For some reason, people got used to calling A1 the longest. That seems to be quite a universal convention, and as a result, you have a decreasing sequence instead of increasing. I don't know if I like this very much, but that's the convention. All right, so you declare this list of log of axes to be what we call the vector value distance. So that's not a real, it's not a positive real, it's a non-zero sequence of non-negative reals. And if you really want a distance in the metric sense, you take the norm of this vector. This is a vector of R to the n. You take the norm. Also, you could notice that the sum of these n numbers is 0. So it really lives in R to the n minus 1. It's 0 because the volume is unit. The volume is the product of the semi-axis lengths. Okay, so that's what you do. You take the Euclidean norm of this vector if you really want to have a distance, in particular one that derives from a Riemannian metric. But in fact, the vector value distance tends to be more relevant, more interesting, and have nicer properties. Okay, and if you ever, I'm not planning to, but I might use the word gaps in this talk. When I talk about gap, I just mean the distance between these consecutive logs. You can think of it as by how much the ellipsoid is smashed between the kth and the k plus first axis. Now, it's important to bear in mind that in general, linear transformations take ellipsoids to ellipsoids. And take this as a definition of ellipsoids. They are the linear images of the unit ball. But they do not take axes to axes. Right? If you consider a diagonal matrix acting on the unit ball, then it's going to take the axis or the main the canonical basis to the axis, so that's fine. If you consider a symmetric matrix, it's also going to take some orthogonal basis to the axis, so that's also fine. But if you consider a non-symmetric matrix, a random matrix, it's going to mess up the axis. For example, if you take this matrix, 1 n01, is going to take the unit ball to some kind of elongate. I should draw this in color. 1 n1 takes the unit ball to some sort of some sort of ellipse that's tangent to both lines, right? This is at height -1, this is at height 1. Can you see my two ellipses? One of them is the unit ball. One of them is the unit ball, the other one is this thing here. And you can convince yourself, of course, that the long axis of this is somewhere here. It has a certain slope, for which there's a formula in terms of n, and the short axis is there. But the slopes of these axes depend on the value of n. So, okay. Now, little b, second way of thinking about the symmetric space. You can say it's the space of positive definite symmetric n by n matrices. This is related to the previous discussion by this SO decomposition, right? When you have an invertible matrix, you can always write it orthogonal times symmetric positive definite. And we had said, of course, that that X, the space X, was G modulo the space of all orthogonal matrices. So S, the symmetric positive definite symmetric matrix, is a canonical element of each class of SLN modulo ON. So that's a nice realization of the symmetric space, just a set of symmetric positive definite matrices. In this language, when you want to know the distance between the identity and S, well, you just list the eigenvalues of S and take their logs. That's the same as saying previously. And if you are interested in the distance between two matrices, none of them equal to the identity, well, you have to write S, you apply S inverse to this pair, right? You apply S inverse, so S becomes identity, and S prime becomes S inverse S prime. When you take this thing, you take its decomposition, S double prime O, and then you list the logs of the eigenvalues of S double prime. There's no really easier way of doing this. There's no straightforward formula that tells you what to do in terms of S and S prime instead of apart from just going through this decomposition. Okay, so that's the more algebraic side of things. But what I'd like to talk about now for a while is what does this symmetric space look like, so to speak, from the inside. Okay. And in particular, what analogies with H2 are valid and what analogies are not, or how we need to extend the constructions from H2. Now, first of all, X is an open ball of the dimension n squared minus 1, so that's topologically not a fancy space. It has unique geodesics due to the sign of the curvature, non-positive curvature. But more importantly than geodesics, it has what's called flats. I'm going to pronounce the word flats a lot. These are, in fact, more important than geodesics. What are the flats? Well, those are subspaces isometric to R to the n minus 1. N minus 1 is what's called the rank, by the way. So when we say higher rank, it means n minus 1 is at least 2. So these are copies of R to the n minus 1 that are isometrically embedded. Maybe I should write this here. Isometrically embedded. So in particular, straight lines inside one of these flats are geodesics for the ambient space X. Now, here's an example of a flat. You take, well, B is the base point, and you act on it with all positive matrices positive diagonal matrices. Determinant 1. This is a flat. So in terms of ellipsoids, it's well, you take all the ellipses that are along the main axis of the frame, and I claim that well, all other flats are of the form GA for G, an element of the group. So what this looks like in general is, well, you take the canonical frame to some other frame by applying G, and then you take all the unit volume ellipsoids along with you via the map G. Now it is the axes of these ellipsoids look deceptively close to GE1 and GE2, right? They're not quite equal to GE1 and GE2. For example, you can see it for this intermediate one. This intermediate one clearly has an axis here and an axis there, so not along GE1 and GE2. And at any rate, the axes should always be perpendicular to one another. And this direction is by choice of G, not perpendicular to that direction. So the images GE1, GE2 are not equal to the axis of the ellipsoids, but they look kind of close, right? And you can make this statement precise, namely when G has large gaps, large drops between one eigenvalue and the next, then, well, the eigendirections are not close, but the flags of eigendirections are close. So in this dimension 2, it's the same to talk about. Well, I should say it like this. If G stretches a lot in this direction and compresses a lot in that direction, then the top, the long axis of the G image of the unit ball will be close to the first direction, but the second is not, right? The small axis of this squished ellipsoid is more like this. It's far away from GE2. And on the other hand, if G stretches the other direction strongly, then this direction is close to the direction of the long axis, and the other one is not. So you can make all of this quite quantitative and precise. And here is a more concrete look from the inside, so to speak, again, so without ellipsoids. Now, from the inside, from the space X, what does a flat look like? So now every point in this flat stands for some ellipsoid. And the key thing about flats is that, well, just like a geodesic in the hyperbolic plane has two ends, it's a line with two ends. A flat doesn't have two ends. For n equal to 3, for example, a flat is a copy of R2. R2 does not have two ends. It has a whole circle of directions at infinity. And what plays the role of the ends is what's called the Weil chambers. So what is a Weil chamber? Well, when you're in a flat, when you're, let's say, the standard flat, so that means you're the image of your points are the images of the standard Euclidean ball by diagonal matrices. Well, you can go and sort the entries of the diagonal matrix from largest to smallest. So there's a whole region here in which they're sorted from largest to smallest. And if you move in any other direction, they're sorted in a different order. So the number of regions or chambers is going to be factorial of n, because it's the number of possible orders for the entries here. And we call the interface between two such regions, we call it a wall. If I pronounce the word wall, I'm always going to be referring to this. So you can notice that, for example, the vector value distance that I spoke about in the beginning is always valued in what's called a standard Weil chamber. I mean, I gave it as a list of reals, but you could really feed these reals into the diagonal matrix and say that the vector value distance is valued in the standard Weil chamber. There's a little bit of an ambivalence whether by Weil chamber we mean these matrices or their logs. I think the word Weil chamber is used for both. And that's one of those things that you have to sometimes decode. But essentially, the distance between the identity and this matrix is the log of this matrix. Okay, here I made a faint attempt at drawing the next higher degree case. If you take SL4, its Weil chambers, well, there's 24 of them. It's factorial 4, it's the number of orders of the 4 entries. And the way this symmetric group of on 4 objects acts on R3 is by reflections in these in the planes through these lines. So you have a cube that's preserved, and you can reflect, for example, across let me choose across this plane. That's a reflection. There are 6 planes that you can reflect across. And I plotted here the matrices that are at the, so these are the logs of the matrices now. At the corners of the cube, for example, this is very singular. You have 3 times the same eigenvalue, so sort of 2 coincidences. There's another special point here where you have 2 top eigenvalues and 2 bottom eigenvalues, and the 2 top ones coincide and the 2 bottom ones coincide. And here's another double coincidence where the 3 top eigenvalues coincide. So this region here, of which there are 24 copies, would be now for us the projectivization of the standard Weil chamber. The Weil chamber is the cone over this thing seen from the origin. Right. I'm trying to summarize this here. In general, the symmetric group acts on R to the n-1 by reflections in some hyperplanes, and the Weil chambers are the fundamental domains. Okay, so I would like to slowly move towards a characterization of how rotations and diagonal matrices and symmetric matrices and so on act on all these flats. So to say this is the main justification for why flats are more important than geodesics in this symmetric space. In PSL2R, the group acts simply transitively on oriented pointed geodesics. If you have a geodesic and a point and then an orientation, you can send it to any other geodesic and point and orientation by, in fact, a unique, so we say simply, a unique map in PSL2R. And this is what survives well this survives well for flats in the symmetric space. If you have PSLN of R, it acts quasi simply transitively. What I mean by quasi is that there's a finite number of elements that do the job. Acts on what? On oriented pointed flats of X. So you take a flat, you take a point, and you take an orientation, which is essentially a choice of Weil chamber. You take one of these 6, for example, is going to be taken by one of the other 6 by a permutation matrix. And when I said that there might be more than just one matrix, in fact, all the other ones that do the job are the same multiplied on the right by diagonal plus or minus 1 plus or minus 1. Okay. So this is what we will mean by orientation of a flat from now on. It means a choice of Weil chamber, so that there are not just two orientations. There's factorial n factorial possible orientations of any given flat. And let's see diagonal matrices. Well, the standard flat was made of diagonal matrices. So diagonal matrices act on A by translations. A, the standard flat. If you take permutation matrices, they act on A by reflections or compositions of reflections across the walls. If you look at an orthogonal matrix, well, it takes the orthogonal matrix, fixes the base point, fixes the Euclidean ball, and takes the standard flat through the Euclidean ball to another standard flat, namely the ellipsoids that are that share a different set of principal directions. So here's a little cartoon. The diagonal matrices act on the flat by translations. The permutations here, I took a very simple permutation and just exchanged two of the vectors. Those act by reflections in the flat. And of course, you have to imagine that there's an action in the whole ambient space X, right, containing the flat. But in fact, it extends. There's a unique isometry of the whole space that extends this action on the flat. And the next thing I want to talk about is how unipotent matrices act. Right? These matrices that are identity plus stuff above the diagonal. What they do is they take the standard flat, pointed and oriented by the choice of the home Weil chamber, the one with decreasing eigenvalues, to another flat asymptotic to A along the directions of the standard Weil chamber. So you have to look at this as completely analogous to the case in the hyperbolic plane, n equals 2. You had these upper triangular matrices, right? One, something. They acted by taking the base line to another line that shares one endpoint at infinity. So now you just have to say you share instead a Weil chamber at infinity. And so here's the flat before action by G in yellow. In gray is the flat after acting by G, and the two flats are somehow, each of them is an isometric copy of R2, right? But they are asymptotic to each other in this particular set of directions. I'm not including the directions along the walls. Those are, in those directions, the asymptotics are different. But if you escape in a direction in between, then you're at exponentially closer and closer distance from the other flat. Right, and of course, if you want to conjugate, if you want to do the opposite Weil chamber, this one, then you have to take the lower triangular matrices, and if you want to take any other random Weil chamber, you have to conjugate unipotent group here by some permutation. All right. And so these are the basic tools, and using those, many tools in constructions from H2 generalized to the symmetric space X. And I'd like to give a few instances of that phenomenon. For example, we had noticed that the region in which two lines in H2 stay close is a long interval that we can estimate in terms of the point of the distance of closest approach. What generalizes this in flats is that the region on which two flats stay close is some kind of polyhedron bounded by walls we can look at it inside one of the flats. It's going to be parallel to, it's going to be faces parallel to the walls. Here I drew every possible situation in the case of SL3. So there's a total of, I think it's 18 of them. So there's a discrete typology of possible ways of in which two flats could come close to each other, right? The largest possible region that the largest possible number of faces that the region of closeness may have is 6. Smallest is 3, and in between you have some quadrilaterals, some rhombi, some pentagons that are the possible shapes. Right? And each of these essentially answering the question. Right? You have the flat A. This is a flat. B is the unit ball. A is the diagonal matrices. So you have one flat and another flat which would be G times A times B. Well, G is, let's say G is close to the identity. So it's 1 plus, yeah. Small entries above and below the diagonal. And what you're asking essentially is, when we conjugate G by a big diagonal matrix, when is it the case that it stays small? Right. I'm going to write this down. You can answer this. Well, it's a certain region of capital A, the flat, in which they stay small. And it's exactly the same as answering the question when these two flats, on what region the two flats are close. So you can do this little game on a sheet of paper for yourself, depending on which of these entries are 0 and which of them are slightly bigger, which of them are slightly smaller. What shape are we going to get here? Okay, a second example that I'd like to mention, because it ties into something I want to talk about at the end, is the cross ratio. So here's a synthetic, well, it's a few synthetic facts about the cross ratio. You remember that the cross ratio is when you have P1 of R, in the boundary at infinity of H2, then given 4 points, you can compute their cross ratio. What it means is you send by an isometry the first 3 to infinity, 0, and 1, and then whatever the fourth is equal to is called the cross ratio of the 4 points. And here I call it beta. So here are some facts about this cross ratio. If you have 4 points in this configuration, infinity, 0, 1, and beta, then you can draw the lines that I did in green and the lines that I did in blue. So the blue lines form a certain angle theta, and the green lines are a certain distance apart delta. And I claim, so this is some trigonometry that you can do as an exercise, that beta, the cross ratio, is related to the angle theta and to delta, the distance between the lines. by some trigonometric functions, cos squared and cos squared. Okay, and on the other hand, so that's one possible definition of the cross ratio and one way of relating it to hyperbolic angles and distances. Now, on the other hand, I could do this thing. I could talk about the distance between this ideal point and that ideal point. Well, I can't really talk about the distance, but I can put a horoball here, and let me choose a better color. Horoball here, a horoball there, and a horoball at each of the 4 points. And I can talk about the inter-horoball distances A, B, C, and D. Right? These are 4 real numbers. And I claim that if we compute minus A plus B plus C minus D, then the result, first of all, it does not depend on the chosen horoballs. And moreover, it's also related to beta. It's log beta. 2 log beta. So, okay, the fact that it does not depend on the choice of horoballs is easy to see, because, for example, if you shrink this horoball, you're going to increase A and increase B, and here you have minus A plus B, so these compensate. And C and D are not affected. Similarly, for all 4 horoballs, they all change only 2 values in different directions, so compensate. And again, by doing some trigonometry, you can check that this S is essentially the cross ratio. It's the log of the cross ratio. Okay, so let us see what we can do in X, right? In X, when you're given 4, well, what lies at infinity here of X is flags. Namely, when you have 2 flags, you can look at the frame that they define together by intersecting the ith entry of one flag with the n-ith entry of the other flag. It gives you a direction, and this set, if you use them as eigendirections, well, you can look at all the ellipsoids that are obtained by taking the standard flat, or the standard frame to that frame. Okay, so at infinity of X are some flags, and we can look at some flats, A prime, and the flats that are asymptotic to them in the forward direction. Again, these are oriented flats, so they have a preferred Weil chamber. You look at the flat that shares its forward Weil chamber with A and its backward Weil chamber with A prime, and then the other flat that does the opposite thing. Right, and again, we can define a thing similar to what I called minus A plus B plus C minus D before. Namely, we take sequences of points that escape inside the flats. So Pn escapes in the negative Weil chamber of A, and Qn escapes in the positive Weil chamber of A. Same for P prime n, Q prime n. And we can compute these lengths, these vector valued lengths from Pn to Qn, from Pn to Q prime n, and so on. And this would be a complete analog to what we had before. The limit as n goes to infinity of these distances. And here's a proposition. I claim that if if G, well, what is G for us? Okay, if I compute, if for my flags I take the repelling and attracting flags of a diagonalizable element G, and also a random flag and its image under G, and then I compute this cross ratio. And what I find is essentially the length of G, not quite, it's the symmetrized length of G. So this first matrix would be the vector valued length of translation of G. It's by how much G translates in its flat. And this is the symmetric, is by how much G inverse translates. And if you average the two out, you get S. So the cross ratio lets you recover, defined in this way, it lets you recover by, well, up to symmetrization, it lets you recover by how much an element G translates. So we get, it's not quite perfect, right? Here we recovered, in fact, by how much G translates. But in general, we found out that we only recovered the symmetrization of the translation length of G. There was a proof of this, but I'm going to skip it because well, it's kind of a computation involving well, decomposing a bunch of matrices as products of a lower triangular times diagonal times upper triangular matrix, and you extract the diagonal factor. So I'm going to skip the proof, and we'll take the break now. I mean, after the questions, if some of you guys have questions, we'll take the break and resume after.
Yeah.
Okay, can I ask a question?
Go ahead.
Okay, so in the very previous slide where you discussed the cross ratio, and it shows the the upper, that's like in the bottom I can see can compute the cross ratio, I guess, and by taking the limit of the four values defined by the sequence Pn and Qn and their primes. So is there any way to choose those sequence, or are they just the arbitrary sequence that converges to the ideal point?
Right, so that's a good question. It does not depend on the sequence that we choose. And the key reason is that the only thing we impose on the sequence is that it escapes along A. It shows the points actually on the flat A, but I impose that they escape inside the positive Weil chamber of A. They do this thing. So in particular, they become exponentially close to the other flat. So if you really want to take well, okay, if you want to take another point close to Qn, but on this other flat, you can take it exponentially close, right? And that's the first thing. And the second thing is that well, if you change Qn, right, you have this Qn, if you change it by an additive amount, then you're forced to change by essentially the same additive amount in the other flat. Again, because they are both asymptotic.
Right.
So the only thing that you need to know is that you stay inside I guess a cone slightly smaller in angular terms than the Weil chamber. Then automatically it doesn't matter. The limit will be the same, and the convergence rate will be exponential with an exponent dictated by the angle here, by how far away you stay from the walls. If you go into the walls, everything becomes bad.
Oh, I
If
see.
you stay away from the walls, it's uniformly exponentially good. That's the philosophy.
Oh, okay, I see. Thank you.